Okay, let's dive straight into something that sounds, well, pretty mind-bending, but it's absolutely real. The Casimir effect.
Mm-hmm.
So you imagine two ordinary metal plates, neutral charge, nothing special there, but you bring them incredibly close.
Really close, yeah.
And get this, they actually attract each other. There's a measurable force, and it's not gravity.
Right, that's the key bit. It's separate from gravity. And all the really precise measurements we've managed so far, they've all been done here, in labs on Earth.
Okay. And the standard picture, the textbook explanation of this Casimir force,
Yeah.
it paints it as, well, the same everywhere, doesn't it?
Exactly. The usual formula, the one everyone uses, it just doesn't have a gravity term in it at all. It implies this force is just constant. Same here, same on Mars, same near Jupiter.
Which I have to say feels a little counterintuitive.
Right.
I mean, think about doing the experiment near a black hole's insane gravity.
Or way out in deep space, almost no gravity.
Yeah. Standard theory says, nope, same force. But that's exactly what the research you brought to the table challenges, isn't it?
It really does. That's the heart of this deep dive, actually. Does the Casimir force, specifically in that parallel plate setup we just described, measurably change if you put it in a completely different gravitational environment? These sources suggest maybe it does.
And the lens we're using to look at this question is this method called electrogravin-magnetic photon radiation, EGM. Sounds complex.
It is a bit technical, yeah. But the core idea, the way it's presented, suggests the Casimir effect might not be totally independent of gravity. It might feel its influence.
And the implications. I mean, think about the future. If this force changes depending on local gravity.
Well, it could be huge for nanotechnology, right? Tiny machines we might want to send to other planets or operate in space.
Their fundamental behavior might change. We might need to completely rethink how we design them for off-world use.
Exactly. It raises some big questions about tolerances and design.
Okay, so before we get into the gravitational wrinkles, let's just ground ourselves in the standard picture. What's the basic explanation for the Casimir effect again?
Right. So at its core, it's about the quantum vacuum. This idea that empty space isn't truly empty.
Uh-huh. It's Belize.
You could say that. It's fizzing with virtual particles.
Mm-hmm.
Think photons, electron-positron pairs constantly popping into existence and vanishing again, fleetingly.
Okay.
Now, when you put those two conductive plates really close together, you're creating boundaries. You're essentially boxing in a tiny slice of that vacuum.
A tiny box for virtual particles. Okay, unpack that a bit.
Well, think of the space between the plates. It's a very narrow gap, right? So only virtual electromagnetic waves, these virtual photons, with wavelengths that can physically fit into that gap or are shorter, can really exist there comfortably.
As the longer wavelengths just don't fit, they're excluded.
Pretty much. It's like trying to play a really long skipping rope in a tiny cupboard. The longer waves are effectively shut out from the space between the plates.
Okay, so you're filtering out certain types of virtual particles, the long wavelength ones, from the gap. What does that do to the energy inside?
That's the crucial step. If you have fewer possible types of waves, fewer modes allowed between the plates, then the energy density of the quantum vacuum inside the gap is lower than the energy density outside the plates, where all wavelengths are allowed.
Lower energy inside, higher energy outside.
Exactly. And that difference in energy density creates a pressure difference. The vacuum energy outside is effectively pushing the plates together harder than the vacuum energy inside is pushing them apart.
Ah, so it's a net inward pressure, creating that attraction.
That's the standard explanation, yes. A pressure imbalance from the quantum vacuum itself.
Now, I remember reading something about van der Waals forces. They also cause attraction between neutral things, right? How is this different?
That's a really good point, and there's definitely overlap in some interpretations. Van der Waals forces explain attraction between neutral atoms and molecules due to fluctuating dipoles. They're always attractive.
Always attractive. Okay.
The Casimir effect, though, derived from this vacuum energy idea, isn't always attractive. Its sign, whether it pushes or pulls, can depend on the geometry of the objects.
Like what?
Well, the classic example is if you take a hollow conducting sphere and cut it in half. The Casimir force between those two hemispheres is actually predicted to be repulsive. It pushes them apart.
Wow. Okay, so geometry is key. That's a big difference from van der Waals.
It is. It suggests something more fundamental about the vacuum's interaction with boundaries.
Now, measuring this force on Earth, it sounds incredibly subtle. It can't be as simple as just sticking two plates near each other, surely. I think I read about corrections needed.
Oh, absolutely. It's extremely difficult. For really precise measurements, like the ones done by Lamoureux initially and then refined by people like Mohideen and Roy and Bressi with parallel plates, you have to account for real-world effects.
That's yes.
Things like the temperature of the plates that adds thermal fluctuations, the fact that the plates aren't perfect conductors, even tiny imperfections, microscopic roughness on the surfaces can change the force.
So they had to factor all that in to get the measurements to actually match the theory.
Yes, and they did. They managed to get agreement within a certain percentage, maybe 1% to 15%, depending on the experiment and setup, once these corrections were properly applied. It was a major achievement.
Okay, so we've refined the measurements here on Earth by accounting for these known local factors. But that naturally leads to the next question, doesn't it? Could there be other factors, things we haven't considered, especially if we leave Earth?
Exactly. Are there other parameters influencing the results that we just haven't needed to worry about in our terrestrial labs? And that's where this alternative view of gravity comes in.
Right, the polarizable vacuum, or PV, approach. This isn't Einstein's general relativity, is it? It sounds different.
It's definitely a different conceptual framework, though it aims to reproduce GR's results in certain limits. General relativity, as you know, talks about gravity as space-time curvature caused by mass and energy.
Warped space-time, yeah.
The PV model proposes something else. It suggests space-time itself has a property like a refractive index, like glass bends light.
Okay, like an optical property of space.
Sort of. They call this refractive index KPV. And the idea is that it's not constant. It varies depending on the local gravitational field energy density. So instead of space-time curving, its refractive index changes near mass.
So light passing near a star bends because it's going through space with a changing refractive index, not because space itself is bent.
That's the PV picture, yes. And in weak gravitational fields, like in our solar system, this variable refractive index approach gives you the same predictions for light bending as general relativity.
That's interesting. So it's less about the geometry and more about the optical-like medium of space itself changing?
Precisely. In the PV model, matter creates a gradient in the quantum vacuum energy density around it. This gradient is the change in KPV, acting like a lens in space-time. The key difference claimed is that PV tries to explain how spacetime gets these properties through vacuum polarization, while GR describes the effects of gravity without necessarily specifying the underlying mechanism in the same way.
Okay, so how does matter do that? How does it polarize the vacuum?
This connects back to quantum electrodynamics, QED. Remember those virtual electron-positron pairs in the vacuum?
Uh-huh.
Well, think about a real electron. Its negative charge will slightly attract the virtual positrons and repel the virtual electrons nearby. It creates a little screening effect, slight imbalance. The vacuum gets polarized around the charge.
Okay, I see that for electric charge. How does that relate to gravity?
The PV model basically extends this. It says that matter, being made of charged elementary particles, collectively polarizes the vacuum. Gravity, in this view, is the large-scale cumulative effect of all these tiny, localized vacuum polarizations caused by the particles within a massive object.
So gravity emerges from these microscopic QED effects, scaled up. Now, where does electrogravimagnetics, EGM, fit into this? You mentioned it earlier.
Right. EGM is presented as the mathematical toolkit that ties electromagnetism and gravity together, using this polarizable vacuum concept as a foundation. And it leans heavily on an engineering approach called Buckingham pi theory, BPT.
Buckingham pi. Sounds like something for simplifying complex problems.
It is. BPT is a method from dimensional analysis. It helps engineers figure out the key relationships between physical variables in a complex system without needing to solve every single underlying equation. It groups variables into dimensionless numbers, the pi groups.
Allowing you to build scale models and predict behavior?
Exactly. And related to that is the principle of similitude, ensuring your model has the right kind of similarity, dynamic, kinematic, geometric, to the real thing. EGM uses these engineering ideas to build its framework.
Okay, so applying engineering principles to fundamental physics, what are the core assumptions, the starting points of EGM?
There are a few key precepts. First, an object just sitting there at rest is assumed to be polarizing the vacuum around it and is in equilibrium with it.
Okay, a constant interaction.
Second, the amount of quantum vacuum energy associated with that resting object is equivalent to its rest mass energy, immensity itself.
Right, the famous equation.
And third, a more technical point. The frequency distribution of that quantum vacuum energy around the object is proposed to follow a specific mathematical form. It's cubic.
A cubic frequency distribution? How does that compare to the usual picture of the vacuum spectrum?
The standard picture often treats the vacuum, the zero-point field, as having a potentially infinite range of frequencies, kind of like random noise across all wavelengths. But this leads to theoretical problems.
The infinite energy in a vanishing volume issue.
That's the one, a major headache in standard quantum field theory. EGM tries to avoid this by proposing the spectrum is actually finite.
Finite.
It suggests the spectrum's properties, particularly its upper limit, are linked to the local mass energy density. In EGM, the spectrum of the vacuum in totally empty space, the ZPF spectrum, or ZPFS, still has that cubic frequency dependence, but its overall scale or upper cutoff is effectively zero if there's no mass energy around.
So no mass, basically no high-frequency vacuum energy.
Essentially, yes. The probability of high-frequency virtual particles popping up is very low unless there's matter nearby to, in a sense, excite the vacuum. EGM modifies the standard ZPF idea by making it finite and dependent on the environment. It does this mathematically by combining the continuous ZPF idea with discrete Fourier distributions.
Okay, that's a significant departure. And the EGM spectrum itself, the EGMS, how does that represent mass?
The EGMS is how EGM describes the energy spectrum specifically tied to a massive object. It's presented as a harmonic wave function representation built from fundamental waves following a finite Fourier distribution. Crucially, the number of harmonic modes is inversely related to the energy density. More energy means fewer, more dominant modes.
And this uses something called the unit harmonic operator.
Yes, theta. It's a mathematical construct representing the number 1 as a sum of these harmonically related waves over time, using a Fourier series. Only odd harmonics are needed. From this basic unit operator, they build others, a massive harmonic operator for mass energy and a gravitational harmonic operator for the gravitational field, each with its own specific harmonic structure.
So mass and gravity get their own harmonic fingerprints, so to speak. Now, the polarizable vacuum spectrum, PVS, where does that come from?
The PVS in EGM is what you get when you overlay the EGMS of a mass onto the background, ZPFS. Think of adding a single particle to an empty universe. Its EGMS modifies the underlying ZPFS, and the result is the PVS representing the quantized gravitational field, acceleration g, around that particle. This PVS then determines the variable refractive index, KPV.
So the mass imposes its harmonic pattern onto the background vacuum noise, creating the gravitational field spectrum.
That's a good way to put it. And EGM avoids the infinite energy problem by setting finite limits on this PVS. It does this by equating the object's total mass energy density with the total spectral energy density of the gravitational field it generates, using the equivalence principle as a key tool.
The equivalence principle, linking gravity and acceleration.
Exactly. EGM uses it to derive the lower frequency limit of the PVS by synchronizing the frequency spectrum of acceleration with the amplitude spectrum of their gravitational harmonic operator.
And the upper limit.
That comes from integrating the ZPF energy density, converting it to a discrete Fourier series, and again equating the mass energy density to this ZPF spectral energy density. A key result is that as you go further from the mass, gravity weakens, the energy density drops, but the number of harmonic modes in the spectrum increases. The energy gets spread thinner across more frequencies.
So summarizing the difference, standard ZPF is often seen as random, continuous, infinite. EGM's PVS is discrete, finite, Fourier-based, and tied directly to local gravity.
That's the essence of it. And importantly, EGM claims these PV transformations match GR in weak fields. They even float the idea of metric engineering. Maybe manipulating EM fields could influence TPV, influence gravity locally.
Fascinating, if speculative. Okay, bringing this all back to the Casimir effect, how does this EGM-PV framework predict a different Casimir force in space?
Well, the crucial starting point is, as we said, the standard Casimir formula has no gravity term. EGM, however, by applying its principles and mathematics to the parallel plate setup, derived a specific solution initially just for a 1 millimeter separation that explicitly depends on the ambient gravitational field strength.
And those initial 1 millimeter predictions were counterintuitive.
Very much so. For that 1 millimeter gap, EGM predicted a smaller force on Jupiter, stronger gravity, and a larger force on the Moon, weaker gravity compared to Earth. The reasoning was that stronger gravity compresses the ZPF frequency range, excluding fewer low-frequency modes.
And in deep space, almost no force at all.
Almost zero, yes, because there's very little ambient vacuum pressure difference to create the force in the first place, according to EGM.
Okay, that was for 1 millimeter. But the recent work generalizes this, makes it work for other plate separations.
That's the goal of the research you looked at, yes. They developed a generalized representation using 3 modeling approaches: unconstrained, quasi-constrained, and constrained.
Right. Unconstrained is just the vacuum itself.
Yes, the ZPF properties across a tiny distance, delta r, in a gravitational field, no plates involved, baseline.
Quasi-constrained adds the geometry.
It introduces the idea of the maximum wavelength, minimum frequency, that could fit between plates of a certain separation, relating it to the unconstrained ZPF, setting the stage geometrically.
And constrained modeling is with the plates actually there.
Exactly. Analyzing the ZPF across delta R with the physical boundaries imposed by the plates, restricting the allowed modes.
How does this EGM pressure behave with distance from a planet?
It tends to zero at infinite distance for a point mass.
They calculate the average calibrated pressure over a practical range, and crucially, the relative change compared to Earth.
And those relative changes are. The headline figures are about plus 37% on the moon's surface, around plus 12% on Mars, pretty much zero change on Venus, then decreases in orbit, about negative 5% in a LEO, down to maybe negative 95% or more in very high Earth orbit or beyond.
Those are really significant percentages, a 37% stronger force on the moon. Wow. What about the accuracy, the limits of this EGM model? It makes some assumptions, right?
It does, mainly assuming uniform gravity at lab scales. They developed an EGM application tolerance formula to estimate the error from this simplification, depending on plate separation and distance from the source mass. Their analysis suggests it might be okay even down to X-ray wavelength separations, which is tiny. They provide tables showing approximate distance and separation limits for different bodies where the model should hold within tolerance.
Okay, this has been a really deep dive. So, boiling it all down, what are the main takeaways?
The biggest one is the core claim. EGM suggests the Casimir force isn't constant, it depends on local gravity. That's a direct challenge to the standard picture.
And it makes specific, potentially testable predictions for places like the Moon, Mars, and Earth orbit.
Exactly. Predictions that differ significantly from the standard model.
The implications, then, are mostly for space tech.
Primarily, yes. Especially nanotechnology. If this force changes significantly between Earth and, say, Mars, any nano device relying on Casimir forces for actuation or sensing would need to be designed with much wider tolerances or perhaps even differently altogether.
So the standard Casimir force value might just be our local Earth value, or maybe an average.
Possibly. EGM suggests it's a local value, and the standard theory might represent some kind of cosmological average needing correction for specific locations. EGM offers one potential framework for how and why it might vary.
It definitely provides a lot to think about regarding fundamental forces and how we build things for space.
Absolutely. It challenges us to reconsider if we fully understand these subtle vacuum effects in different gravitational contexts.
So the final thought for you listening, given these potential variations, how might our fundamental understanding, and even our engineering for space, need to adapt? It certainly makes you wonder if the constants we measure here are truly constant everywhere else.